Alright, so modular engine block system. A good way to put this is essentially like a Lego set for engine blocks. I know that sounds kind of weird, but it's effectively all I'm thinking about it as. And all that would really ultimately mean is, see here, delete this and this, those things, and this one too. Yeah. All right. Right. So if you have a CNC, we're talking about, and I'm just talking like a mini one that you can probably build with some threaded rods, some basic electric motors, and some open source software, online, and most likely some 3D printed materials. You can easily probably make this within tight enough tolerance and specs. But that's me, right? And the guy I am. Most people probably wouldn't think that way, but that's is what it is. So all a engine that's a internal combustion engine piston engine is a cylinder that's tight enough tolerance with a piston head that's attached to a crank and some in and out, which is like a two stroke if you want to do the piston that way as the valve, or uh, you know, valves that are at the top or along the side that rotate or go up and down or slide. It all depends on what you want to do. But I tell you is this one's pretty simple in that if you know how like a single cylinder works, then it's essentially going to be a version-ish of that. And if you've ever seen how a Winkle engine is threaded and bolted together, then it's essentially a modular engine to begin with. One side, another side, and then the big old bolts, and they squeeze them down, and it doesn't come apart, right? If you don't know what that is, that's okay. Most likely, you're like the vast majority of people that don't know anything about engines. So, no worries. A Winkle engine is a bunch of stacked, like, blocks of aluminum and some gasket material, and thread a rod through it, and then they bolt it down on either side with the rod. And then it's squeezed together, and then now it works as an engine because there's an axle in between every one of the blocks. Is literally what it is. Pretty simple stuff. Now, this is kind of a similar version of that, except we're going to be using pistons instead of using threaded rods and some stud bolts and so on. It's more of a coolant sort of quick disconnect line with some basic kind of, it's a good way to put that, for the crankshaft, because I hate crankshafts and they're annoying as fuck to have to build or machine or anything. It's just going to turn into a gearing system. It has an axle attached to it with a bearing in between each one of them. You'll bolt it at the top and you'll bolt it at the bottom where the crank is, where the head is. That'll be your girdle. The quick disconnect. I'll have a gasket right in between, and then you can effectively just bolt on a head. So now it's modular, and you're able to effectively build it how you'd prefer, right? Get the spacing and get the length and the number and all that down for the sizing of your under or over square or square cylinders, the head shape, the way you prefer, right? Now, um, that also means that you can modularize your heads, and it's a bunch of bolts. Just what a lot of people would do. I don't want to do bolts. Mine's going to be a sliding on latch system with the quick disconnects. So if you know anything about like how chair legs or table legs, anyways, you press the button, you pull it down, it pops into another side of a hole, right? That's kind of the same thing. Like you press it in, you slide it, it's got a spring, and then once it goes into the hole, it then opens up, I guess. It's a good way to put it. And the two surfaces, well, they go into each other, right? Pretty simple stuff. Should be understandable. But that's a sliding latch, right? You hit the button in the right place, opens up the latch, then doesn't allow for it to move up, down, left, right, in any Z depth as well. You don't need to machine it to insanely high tolerances. And because each one of the gears between each one of the cranks happens to ultimately be within tolerance specs, that's all you need. As it moves from top dead center to bottom dead center, it's still going to rotate around. But that kind of looks like effectively a conical sort of piston, right? Differential that goes up and down. Sort of a thing that we already have for suspension. So it's like, well, if it can do that, then it allows for you to seat them in that and still allow for it to rotate just fine. And still transfer each given power stroke and time it as you prefer. And even change, depending on the gear type that you like, how it accelerates up and how it accelerates down. Changing its version of a top dead center 12 o'clock rotation to 1 o'clock that suddenly increases its acceleration down, eliminating some of those issues. I was thinking about it because it's like, well, this would allow me to use aluminum and iron in multiple places, as I could seat them together like a puzzle piece block. And then I'd be able, as my dog tries to fight me, like, freaking pay attention, pay attention, pay me, pay me, hey. Anyways, um, to prevent some of the warping issues that overheating blocks can have. Again, don't really need to worry because I can bolt it at the top and at the bottom while still having a surface that has a area in the side of the box that has a latching quick disconnect system. Luckily, because of how cheap it is to manufacture like little tiny CNCs yourself, if you got a 3D printer, you know a little bit about any of it, you can do it yourself. And you can make pretty substantially sized parts and even manufacture 3D printed parts inside of these things that would allow for you to still be strong enough to make damn good power, you know? It just needs to be strong where it needs to be strong, and the rest of it just needs to be strong with the heat and movement of water and everything else. You can cut down on weight and ultimately allow for the slight amount of vibration, right, as it goes through to be absorbed effectively. Because each individual module is now good to go. We're just adding each one of the power strokes together, right? Which means balancing can be easier, along with allowing for boost and cooling and everything. Easier to take it apart. My problem is the bolt system more than anything for like most people. It's like I'd rather and prefer to have a bunch of bolts that go through all of it. And it's like, yeah. Yeah, that sounds like a lot of actual fucking tightening of bolts that I don't really want to do. Or in this instance, studs, really, threaded rod stud stuff, which again, I just don't want to do. Sounds annoying as fuck. You know what I mean? So it's just like, I'd rather just slide it and then bolt it at the top and bottom, use the heads as essentially like a sort of, you know, um, clamp, I guess, at that point, especially with a crankcase that you're gonna have to make too, which really isn't that hard, truthfully. Because it's like, well, this side and this, oh, I've got this, area you just take off, and then kind of like the differential for an axle, cover, right? It's like, all right, well, instead of having a bunch of bolts there for that one, this one is much more of like, I'm going to be able to effectively slide it off, and then I can bolt it in the main areas I need to, right? And then everything's got effectively, there's those little barb ends, right? Like a quick disconnect kind of thing, because it'll still hold like all the oil. You just want it to be strong, right? And so it's like that'd be the girdle, and then like the bolts and where the gears are, right? That would be there, and then crankcase is just going to be a big solid piece that allows for all of it to bolt as per normal. And you can always just make a bigger piece if you wanted to, right? Not that hard. So, um, I don't know. I was just thinking about it because it seems like it'd be really easy to just do this, right? Like this would be a cheaper, like instead of having to CNC a whole bunch of things, which is what I'm talking about. But it's like, yeah, no, for your own, you know, like shop or home. Like if you have a house or apartment or whatever, then it's like, yeah, well, this basically exists on a table somewhere, and this will do it because it's effectively like the size of a gallon, milk or water jug or some shit like that, and that'll give you everything that you're looking for. You just do another one, do another one, do another one, do another one, and at the end of it, it's all bolted and it'll work. Instead of I need to dig a hole and I have to melt this steel or aluminum. You know what I mean? So I don't have to do any of that. I just need it to be within tight enough tolerance. I can go a little bit over, and then I can machine it a little bit, right? To spec. It's not hard to get gears off the shelf. It's not hard to get bearings that'll make sense for this at all. In fact, none of this would be that difficult to put together, which is the whole point of it. Like the concept, yeah, it just wouldn't be very difficult to put together. And you can easily produce like the opposed piston, or if you are willing to use those gears in between, you can make a modular block system where they're side by side. Like let's say it was, uh, instead of an inline four, you have an inline two right next to each other and be a square. You have intake coming in at the top, and you can still have it going off to the sides, right? And then it goes to a central gearing for your pistons, and that just needs to rotate the correct way and have the correct geometric is the word I was going to use, but geometry is really the word that you're going to use. So that way it allows for the correct stroke length. If you used a post piston, then it's like, well, yeah, sure, it's this length, but actually you have to have it, right? And so now you have like a short stroke that acts like a long stroke because, of course, well, you got two of them that acts together to equal one full stroke, right? And they're more efficient in general. You still have cooling, which great because it's like, well, yeah, I mean, a gear that's there with a little bit of pivoting, action for geometric angle stuff will work astoundingly well for a system like that. So it can be highly compactified because that's effectively a gear pump already, right? You know? So I don't know. Seems like it'd be a good way to get around some of the major shortfalls of some of our current designs in motorcycles, subcompact cars, you know, stuff like that. Because I can easily see this making like 150 horsepower, especially when you don't have to worry about balancing the same way. Like balancing for like a tiny little engine like that becomes vastly different, right? Like it's because of the gearing that we're talking about and because of the way that we can oppose piston and then have one side rotate separate to another side, right? In an oppositional, meaning, counter rotate manner. That means you're able to get like a central axle that works off of everything. And that does mean that you can then use that as a rotation because it's right next to it, right? So a rotating valve, which is like a ring valve, so like a bearing journal on our regular piston engines, right? Then that can rotate around the cylinder, still have intake and exhaust still occur, a four-stroke cycle still happen, and still have everything work as per normal, be easily taken apart, which is great, last for a decently long period of time. It all depends on those materials you're using. For me, that's really what those tend to be. It's like the better the material, the longer it lasts, the better your tolerances, also the longer it lasts, but also that lubrication, everything, right? So it's like you do it right, it'll last for a really long time. You do it, okay enough, it'll last for a pretty decent amount of time, and then you're gonna have to service it, which luckily is pretty easy to service. So, you know, I'd prefer it, but anyways. I was thinking about it because it's like, well, that allows for those rotating ring valves that I want, right? I love opposed pistons. Opposed pistons are big, like, upgrade in my mind for engines, just because they're one of the easiest ways to force higher degrees of efficiency, right? So if you're able to do an opposed piston with the exhaust recycling off to the outside areas and have that be, like a part of the, you know, sealed, like up and down because of the way you can rotate it now, then it means you're able, instead of like super compact, you're able to get away with some of that exhaust to help with efficiency and the outright torque you're going to see. Then you also have the ability to fully balance the system with a lot better um, gapping tolerance, right? Like the stress and strain it sees isn't going to need to worry about anything going against the piston, a cylinder sidewall or the piston, right? Right. So long as you don't hit anything or you take a really sudden sharp turn that really kind of just sounds like you You rolled. I'm just stating some obvious facts here. Suddenly, a sharp turn. There are some twisting motions. There might have been some twisting motions. Anyways, uh, but that also means it's a dry sump compatible system. It also means that it's much easier to balance to those high RPMs, and I don't need to worry about boosting it nearly as much. But I could still boost that, right? Like my hmm. Anyways, the point I was trying to make was now I can force it into like a Fiat 500, a smart car, motorcycles, you know, small little compacts that right now, if they're like 150 or something pounds, it doesn't seem like a lot, and that's a probably really good light engine, right? But if I could get rid of like half of that weight, that would be way better, especially if I can provide the same horsepower and torque, right? Especially even better being that I can force it down low and get it closer to where central weight distribution is, which can help with the feeling and handling of the vehicle and the safety too. So that's my thought process on it. Um, but that's because it's effectively going to look like a box. Like if you look at it, it's going to look a little bit like a box. Yeah, you're just tiny little box. You just stick it down there, just in there. I got 150 horses. And it's like, yeah, probably pretty easily. I mean, it really depends on like what we're talking about for displacement, boost, fuel, and like how you make the power. So combustion is a big part of that too. An opposed piston with an exhaust recycling into the outside that then goes off into like a regular exhaust cycle is like big, for diesels, right? Like diesels love that, right? But diesels are fine with heat so long as it's treated correctly in a way that doesn't overheat the engine, right? This, it's like, well, I could get away with it, but I'm gonna have to worry a little bit. So it's like, hmm, my immediate go-to is the nitrogen filter stuff that I've been getting into along with the super turbo stuff that I love. And so I need a intake manifold to begin with. Well, intake manifold is a supercharger, but a supercharger that's not a normal supercharger because of course exhaust recycling, right? But yeah, but it's also the thing that makes it so that way my valves rotate. And depending on its speed of rotation depends on what my valves for because they're rotating along the cylinder sidewall in the center, right? That means it's going to be near perfect center, and then it'll go up, and then it'll open more, kind of like a lift, right? But also depending on its RPM, I can have it delay and stay open for longer. This is something you want, right? I can also have it start opening sooner and then delay, and that's based upon gearing and based upon a rotation that allows for that gearing change, right? I've been doing that in a lot of my other engine designs. Uh, but nitrogen filter, we have high flow, and I found one of those. And by we, I mean they manufacture that, so like it exists in the world. They have a high flow nitrogen filter that's good to up to like 60 C, and I forget what the bar was, but a really, really high boost. So I was like, well, that'll work. I just need to filter the air a little bit before, and we have air filters, so that'll work. And it's like, right, well, the nitrogen can now go into the exhaust going into the sides from the center, okay? Right? And then that'll go off into turbines, right? That have to attach to the supercharger. So like the supercharger is like it's based upon the axle, right? But it has to go from the center. I'm sorry, the top here, right? And then it has to get fed in, right? And that's fine. It's not a big deal. But it's like, well, if it's rotating, no, it's a statically fixed object. It's like, right, yeah, no, well, it is. It would be. But what if I wanted it to be my camshaft that sucks in air? They already have hollow camshafts. No one said I can't use that to suck in more air. Just because filtered nitrogen comes out one area doesn't mean that the rest of it doesn't go out somewhere else, right? So it's like nitrogen has to go somewhere. That's fine. I'll separate that to the oxygen-rich air, and apparently it's pretty efficient at filtering out the vast majority of nitrogen, which is great. But there's other stuff, argon, but we're talking about a percent. So it's like I don't really ever care about that. It's really about the fact that burn propagation is incredibly fast the moment you have higher oxygen, right? Which usually means you have to treat the intake port and the um, you know area where all that's coming in, because it's very high oxygen for manifold, plenum, all that, in some sort of an epoxy, which is what I talk about in my natural uh, aspiration nitrogen filter tech video. Anyways, so it's like that would allow me to not have to worry about the oxidization, rusting, right? You'd normally have to see. I can still do port and direct injection through that, right? Which is fine. Then separation would be down to either side, right, from the filter, depending on which cylinder would be firing. That'd make it easier for me to pulse an equalink tube the nitrogen into any given exhaust cycle, helping cool it down, but increase during that as well. It's given pressure because of the density. There's a lot more nitrogen than there is the exhaust, right? So pressure remains nominal, which is great. You're going to want that. Not to mention, during that, I can do a 6 cycle, right? Inject nitrogen, pure nitrogen, or very close to, into the intake during that exhaust. It can produce a scavenge, but also to absorb some of that heat back into the nitrogen, and then during the next intake for regular combustion, it absorbs the vast majority of the heat from the previous exhaust from the cylinder sidewalls, but also because it'll go through, back over the same areas, right? But also provide another hit, I guess, quotation marks there, to the turbine, which is what I've normally done, right? And so now I have a 6 stroke cycle that's able to be cooled more than enough. I don't have to worry about like a water stroke cycle, right? Because it's nitrogen, there's no oxygen. So that allows for the turbine to remain pretty darn efficient. Supercharger is really just a um, multi-gear. I always use a gear, like a transmission. It's like on like a scooter, called a venerator, right? It's effectively a CVT. That's all you need to know about it. It's essentially attached to that, and then once it gets to the right RPM, or the exhaust has been able to spin the turbine, okay, enough, then you're able to, which that could be a big round one at the bottom actually. Now you think about it, because it's a cube effectively. So it's like I can get a big round sucker, right? It's like I can feed it from the top and bottom, and I have to equally tube those to the sides, right? And then all four of those go into one. And I can get that to give me a much different type of setup. So it's like a very large, right? But they think it's like a snail. I'm not a big fan of the snail stuff. See, I really don't like them. And technically, it's lower pressure, right? And the larger they are, the more mass, of course. Cubelet theory still remains the same. Doesn't go anywhere, unfortunately. So it's like, all right, but I can get something from that that's way more efficient if I make it larger and made for that. So from both sides, I can feed them in, have it rotate down towards the center, and then that center can be a center outwards hourglass like we have for bigger turbines. And then that gets fed off into our catalytic and everything from there. So sort of like a medium pressure turbine that goes from out to in, like a Tesla turbine that heads towards a standard stator and hourglass low pressure turbine system. I suppose that'd be like a crank or whatever. Yeah, something like that. Anyways, the top, of course, they've got the compressor, right? But compressor-ish, right? So it has to go through the nitrogen that has to separate at the front off to the two sides, right? From there, it goes up to the top, but I don't want it to actually, uh, see here. So I'd have to put this more towards the front then. You have to push compressed air through the nitrogen. That's right. I always put the nitrogen filter into the the manifold actually, because it's way faster and easier. All right, so nitrogen filter is not going to be in the front. Compressor would be near the front. We'll use a water to air cooling, right? Because I'm going to have the gear pump right there anyways. So that'll just be its return line. That'll go off to the nitrogen filter, which will dump the nitrogen off to the sides. And then, because I need it to head towards where the intake is, then it's easier for that separated air to head forward and then down to the sides to a rail-like system, right? And so that means I could probably, like with a supercharger, have two sides of water cooling right there for the oxygen to redensify, because it has to go through the filter. So the filter will warm up the air again because it takes energy to push it through, right? And so a little bit of a cooling, and then separating that into each individual area with a separate rail that will go from that pressure area when it opens off to the next pressure area. for, the firing order, yeah, right? So it's like that'd be easy enough to sneak through because it's a modular system. The the inside of the little box here, right? So like I can sneak that through, and then that allow for a system where it kind of constantly recirculates and wraps around an oxygen pressure wave while it feeds in another one, right? So it maintains a higher pressure overall consistently to the next firing order. All right. And then, yeah, that should be done. It's just, yeah, it's just placing the flywheel and clutch system and then strap it to a transmission. The turbine will help with the intake for the compressor because it's right there anyways. But it's like once it gets to a point, it's like it can just easily dump it into the crank, right? Because it's right there to begin with. So it'll just dump it either directly into the compressor, and once that hits a point of mechanical, yeah, I don't want to go above this RPM, it then just adds itself into the crank. That's like a clutch or whatever system, whatever you need it to be. And then, yeah, okay, so I got the exhaust for piston directly into crank, and then turbine directly into crank. I can make this pretty small for what it's worth because I would have like an opposed piston, like it's a longer stroke, but it's a shorter stroke, so I can rev it pretty high as well and run it still pretty fairly boosted. Yeah, and then I'm usually the I'll more or less dump a bunch of fuel after the initial burn. So I run super lean, right? And then I can burn. Well, no, because it's oxygen rich and it'll explode actually. So I need to get off of that. Like burning oxygen after. So if I burn, yeah, well, I have direct injection. That's true. I already, I mean, if I might have nitrogen injection, well, that's more of the port than anything else, right? When it opens, yeah. They'll just seal off one end for the oxygen, and that pressure wave will go off to something else for the next combustion cycle. It's a six stroke, so there'll be a regular combustion while there's a nitrogen reabsorption of heat cycle going on, while an exhaust cycle is heading into the turbine, right? Meanwhile, any excess nitrogen constantly goes into the turbine anyways to keep it not obliterating itself under that kind of heat. So that'll be fine. But then it's like, all right, so I can usually dump in more fuel that I want because that's fine, right? And I'll just use a gaseous direct injector from the oxygen and then burn oxygen after an initial burn. That way, the initial burn's heat will absorb into the fuel. It'll decompose the fuel pretty significantly, making it pretty easy to burn as it's going through its power stroke cycle, which is what I talked about in the natural aspiration. I remember talking about it back there, but like fuel likes to explode when you direct inject it after combustion in an oxygen rich environment. But oxygen means you can pulse it and have specific burn moments. And instead of it exploding and detonating, which it can do that still, you can be a lot nicer with how much oxygen you're going to add in. And so it'll burn, and it'll burn quickly instead of explode. because fuel will like try and atomize, right? So oxygen is like, well, there's not enough oxygen, right? Like for the fuel, right? And so like the fuel is like, well, there's a little bit of oxygen, it immediately burns, right? But then it'll move as it's expanding, right? And then you can pulse it in, right? But fuel will all of a sudden rapidly decompose and burn. So you can tailor how much oxygen and burn you're going to want. It'll still burn very rapidly, but it all depends on how much fuel you're going to add in, right? So a good way to put it is if there's not enough, it burns slower, right? It'll still burn very fast because it's oxygen rich. So, anyways, that'll be doable so long as I use some quartz, high temperature quartz and material in those injectors, just upgrade them a little bit, grow them out, put some quartz in there for the tubes. Yeah, this is what I was talking about in that last video. I just need to make sure I get the 3 piston rings. So yeah, I need an oil piston ring as per usual, right? And then I need the 2 on one side for the bottom and 3 at the top, so 5 total. I suppose I can go for the full 3 and 3, which wouldn't be impossible. I usually just cool the piston heads and um, connecting rods because I can usually just make them out of a solid piece by making them hollow. And if they're hollow, then it's like, well, then that's just, oil as a pump that goes through it. So it's like you'll push oil into it, it'll go up as it moves and it goes up and down, right? But it's like that's one side is the entrance, and at the bottom, the other side is the exit. That's the, kind of standard one-way valve setup that you can run, and then it recirculates through the hollow piston and in the head instead of having to spray it around the outsides of the cylinder sidewall, which is usually what I did. Now I can just recirculate it, and a little bit's still going to go into the oil rings, which will be fine. And then the sealing is for the top and bottom, the sides, that is, right? Then just needs to be piston rings, you know what I mean? That are pretty high gap, or a pretty small gap, but very high tolerance, I meant. Right, you'd probably want to use like 3, 4, 5, something. Make sure it really doesn't have a lot of blowback. But you can always run because you have a turbine and a compressor, a vacuum on those things, right? So and it's got more than enough oil. It's got the heat density, but you're cooling with the nitrogen, so the nitrogen should be fine. But you are gonna have to still cool it as per normal instead of being able to get away with nitrogen cooling it completely. You're gonna have to cool it with like a slightly larger radiator and an oil and all that cooler, right? Yeah. And that should give you a real high power density, power to weight ratio for what it's worth. Um, hmm. That should do it, I think. I mean, I could be in the maybe upper 60s, possibly 70% work energy capture from a regular piston. But that's just because it's not technically that. It's really the turbines helping do the work energy too. You know what I mean? So, because like people don't know about the exhaust like for the piston. I'm not getting extra power there. I'm not recapturing it technically. I'm reducing parasitic loss. Okay, so it takes energy to suck in from the flywheel to then make another power stroke, right? And energy from the exhaust stroke to from the flywheel to exhaust things, right? Otherwise, it just stays there at the bottom. If it doesn't store energy in the flywheel, then ultimately you get nothing from it. And so this exhaust gets placed to the outside, which will help reduce flywheel weight. And then the flywheel weight can be taken up by having the turbine from the super turbo combo become a part of the flywheel, right? And then it does work energy. It'll recapture and then it'll add in. And so the exhaust on the pistons really just helps reduce flywheel weight and parasitic loss, as it'll try and balance the energy that it takes to intake and exhaust from any of the other given not, cylinders, right? Pistons during its firing order. Now, that's pretty simple and easy to understand, right? But it's like, behold, the next modular system because it's, I mean, so what? I can't just put three next to each other and have like an inline six or something? Or how about just a straight six? Yeah, I mean, I can basically do the same thing. You know what I mean? And so, like, that would work. I don't know. I'm a big fan of torque. Torque is really what the measurement of any of the power is. So it's like if you can capture in any given power stroke the maximum amount of torque, right? Then it turns into RPM. And if you can't make high RPM, the standard go-to is gearing. If you have overdrive gears, then you can make up for a lack of RPM by having higher, uh, you know, RPM through gears, right? But you need the torque to do it. So for me, torque is king just because I can now use less fuel and burn less in terms of my material over time. So like the engine lasts a long time, right? And then it's all about gearing to make it efficient in the application that you're looking for, which is at like, regular street speeds. Okay. And it's going to become more efficient at being able to deliver both that power, but use less fuel to effectively be at those speeds because of the torque that's there, right? Now, that also tends to mean, though, that we end up having fanciful claims from people that learn how to do this, where they're like, I've got 100 miles to the gallon, 100 miles to the gallon on my tiny little. Look at this. It's a tiny. Look at how small this bad boy. You know what I mean? And it's like, yeah, but you're not talking about how kind of dangerous it is, isn't it, to get up to speed, huh? Just a little, right? Yeah, and that's because gears that we have now and the way they deliver torque on average for gasoline in this instance is not set up for it. It's just not meant for it. It's engineered for the way it delivers power normally, right? And so uh, when I see that on YouTube, I find it interesting, and it's like, well, you're almost there. You almost got it. You know what I mean? You need a high-low gearbox, right? You need a high-low gearbox, and you need also to um, remember that you don't need to have high RPM. People are trained to hear an engine go to a higher RPM and believe that they are now, getting a tremendously higher amount of power because they are, right? But they're not using the power that they currently have very efficiently, right? Like torque allows for them, even if it's a lower RPM, so long as that there's extra torque and energy within inside the flywheel to continue sustaining what they need to gear it such that they can have an overdrive that allows for them to get to that speed just fine. And that usually for a lot of people um, will be just fine, right? But it's not for everyone, of course. And if you want a higher RPM to perform those given, types of you know, torque and horsepower figures, well, yeah, no, you're gonna need to make sure you rev it at a higher RPM because your engine will suffer. You'll get larger knock probability, right? There's like low RPM engine knock, which is not great, right? And if you don't make sure to take your engine up to a little bit of a higher RPM, especially if it's built for it, then your engine can actually suffer. Because it's just gonna burn more fuel than it should. Uh, a good way to put it is it's running rich, right? And deposits can happen, and effectively a bunch of crud can build up and more. So you don't like that. No one likes that. You don't want that, right? But if we're talking about maximum efficiency, then diesel, while it's really good, is heavy in many ways. Like the engines are heavy. It's just what it is, and they're designed heavily for longer strokes, right? Or those higher compression ratios. I often design my engines for a low compression ratio that burns after. And then that gives me the equivalent, like I compressed it further, right? And accelerating it after top dead center, which normally is not a great thing, right? But the mathematics and physics of a internal combustion engine for their way of describing how torque is applied through these gas laws and all this other stuff looks awfully completely ridiculously over the top as math to me because I go, so F equal ma, huh? So F equal ma still F equal ma, F equal ma still F equal ma, F still equaling ma, right? Which, if you don't know what that means, is force equals mass times acceleration. Except the thing is, it's squared, right? Yeah, right. Now imagine force is that piston mass accelerated through this given pressure. Now, pressure changes dynamically. Now, if you want to damn it, Phaser. Stop going after my arm. You want to accelerate it for longer, square that acceleration. But once it started to accelerate, it's easier to continue accelerating. Newton didn't change its laws, as far as I'm aware, which then means burning it after, which always introduces more heat, right? But it's like, right, yeah, well, yeah, right. What's the distance it's traveling? Well, huh? How long is it experiencing the heat? What are you saying? You know what I mean? This is what all internal combustion engines end up understanding. You know what I mean? For the people that build them. right? That is, the people that build them end up understanding about internal combustion engines after a point. The gases burning are not what you usually worry about because that's such a small period of time that it's not as significant as in RPM that's so high that friction is what you're worried about. All right. So, but if the temperature exceeds a certain point, of course you have to worry about that. Right. And there's a obvious direct um, ratio to given amount of heat to given amount of pressure given the same density, right? But if density changes over time, heat remaining equal, of course, then in an expanding volume gains higher pressure. A good way to put that is the heat can't go above a certain point. There's no getting around that, right? But you're also introducing a remainder of the heat as it's expanding while introducing more density too because of a increase of the gas that burns during that moment. Take it into context as a rocket fuel. You have a given delta V. There's a delta V inside of the cylinder. This is your rich mixture of gas. You only have this amount of oxygen. Well, that means you only got this amount of specific impulse for your delta V. Now, add in more specific impulse and you extract more and more of your delta V. F equals ma squared. The acceleration gets squared because it's accelerating still with the given energy that you can still get. The Q value of the given fuel you can still burn. As it expands, yes, the heat drops, but if you maintain the heat but increase density because of the given gas that you're introducing, you're now able, during expansion, to maintain acceleration, increasing your force because you can't increase mass. The mass of the piston and its rod maintains as is, the same. Now, because the gears for the modular system are what they are, it's fine with having that go on, right? Not every engine is going to be designed for that, but there's a point where it has to decelerate, which means you can't usually, although everybody's different, they all have different styles of ways of producing and having that power added. My gearing best that I've ever gotten is always at max been like a 90% of a force before it basically turns into a suicide wall burn. Like it's like, no, it's a suicide burn. No, 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 that's a wall. Boom. And then it stops. It's like, no, I'm fine. Boom. So it's like typically you can do 50%, right? 50%, and then it has to start decelerating. This is rocket stuff before 50. So that's the Lagrange point of the halfway in between your halfway, which is a quarter. So you can accelerate to a quarter, then you have to start decelerating to the half, and then you have to fully decelerate by the time you get to bottom dead. You can no longer accelerate any further past middle, is what most people think. But what I found is you can do 59, 60-ish. But by that point, because of the way most cranks are built as it rotates to that point, you're now going to hit a you're going to effectively try and push the rod through the crank, right? Like where it's connected. and it doesn't want to do that. It's like it's still fine, moving down because it's off to the side. So it goes from its version of 12 o'clock, and as it goes over, it's like able to fall still. But the moment you get to around that 4 o'clock, 5 o'clock, it's now going to knock. You hear it? It's going to hit something, right? Gonna boom, 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 right? And that doesn't work very well, right? Now, pistons are only able to do that, and that's a very specific setup, realistically, right? For any given engine, internal combustion engine. For a standard rod and bearing journal crank setup. This is a gearing setup. That means I effectively have to deal with it as more of a CVT like idea. That means instead of, oh, I have to worry about these analog free fall moments of as it curves and arcs towards its bottom dead, and at the end of this arc, it's going to start pressing more and more on the inside corner of where it's connected past its middle. This one is more of a, yeah, no, 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 that's not the, no, 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 no. I need to make sure the teeth aren't broken off, and I definitely need to start decelerating it at exactly the right time. And at most I've ever managed to get is that 90% wall. Because if you don't hit a deceleration moment, all you do is you break your teeth off and you have a rod that's going through your crankcase, and you don't want that. So, the best teeth I ever designed for something like this only managed at most about an 80-ish to 87, 88, really more of that 90% range. But it's a wall. So it's like, it's never really worth it to go past a 55, 52% area of acceleration continuing, and allowing for deceleration past that point is just fine, right? Instead of a suicide burn where it gets all taken up in a very short moment, which is highly stressful for any material because it impacts it. You then decelerate it more slowly at that point, right? And then, because of the way I usually design my gears, I typically have a real weird difference for how I balance it. So like that's harmonic balance, like secondary imbalance and so on, right? So I don't want it to accelerate too quickly from bottom dead and top dead. So like I remove some of that top dead, but of course it has to go into something, right? And if it's going to extend, if I'm going to make it extend past middle dead, then of course there needs to be a sudden increase, a speed up on its return trip to its top dead, which coincides with the continual acceleration, which essentially means I have to balance it off of my combustion firing order. So they're fine with balancing off of each other, right? Because they're just up and down. And they'll do it in such a way that they're perfectly balanced like that. But the harmonic imbalances then have to be balanced off of the accelerational aspect of every given piston, because it'll suddenly yank up, right? And the only way that that's balanced is if I'm still accelerating down with another piston, right? Uh, and if it's not there, I have the compressor as my balancer. It's not even a joke. My harmonic balancer is a compressor. It's a gear type of thing. I know that sounds so weird, but it really is literally what I do. It's it's oh yeah, no, I'll just suddenly yank it. I'll just suddenly yank it down. Like I'll slow down or speed up the compressor a little bit through a gear. Yeah. So it's like, well, if it's already balanced, then it doesn't have to worry. But if it's not and it's slightly off, then it'll connect and then it'll yank it. It'll slow it down or speed it up. But that's because it's connected directly to the crankshaft, which even then, jeez, dog, even then, I use harmonic, or not, Formula One was an inertial dampening suspension. So as it goes up and it goes down, it has to rotate something, right? And that's, going to take a given amount of force, and a degree of that is going to be soaked up. There still needs to be a counterweight system, but what I found is like you can get away with like almost nothing if you do that. And since I need you know, a axle, crankshaft, right, all that, then it's like, well, it can be hollow. And since it needs to balance off of those things, then it's like, well, that's two of these inertial dampeners that are in the hollow, which can also help with pumping fluid around, as they have to inertially dampen things by rotating slightly. And since it needs to be balanced off of something, right, there's a bearing and that has to move forward and backwards, and that's a fluid resistance. Those are holes that's, now able to hold the crankshaft very, very tightly and very well, right? Like a supportive structure inside and outside and on the ends. And so now it has multiple spots of contact, making it stronger. Essentially, even though it's an opposed piston little box engine, it's like, oh, you can get 150. What are you really getting out of that? Well, I mean, I can easily make it produce 900 foot-pounds of torque if I wanted to, because of the acceleration. See my explanation for starting and priming, and then here, F equal ma squared. Not to mention I have a mass, that's the turbine, and then the outer, pressure as it, of course, has to be moved out of the way or is going to fill in that area as it heads back towards the center, right? Which will help with that, but it doesn't make it suddenly, because that's the parasitic loss, right? Have more torque. It reduces parasitic loss of torque, and so you get that torque back that you normally would have had, which is good. But then the exhaust goes into a turbine, and if it's traveling fast enough, like a flywheel, it adds its torque from its given pressure. Same thing with the nitrogen, as it helps cool it and redensify, right? It's all to say it has a high torque for a six-stroke engine that can rev really, really high because of post piston, and it acts like it's under square, which then gives it a much higher degree with the gearing for our crank here of tunability for balancing to much higher piston speeds. Because I don't have to worry ever about valve float or it getting too hot because, of course, it's cooled and lubricated by the engine coolant and engine oil, which has to be there. It then means basically suck it to anyone out there that's like, well, I have to worry about this, that, or any of these other things. it then turns into, uh, well, yeah, whatever the material design can handle, that's what that could really be. And for however long you want it to handle it for is what you're going to look into. So it's like, "Ew, it can handle this." It's like, right, for how long? What's the material strength design of this material? And in that graph, suggest it can handle this type of stress and strain in these load areas for this long. Um, it's like, well, let me just do. So I can hit like well past 25,000 for hours and hours and hours and hours and hours and hours. It's like 900 foot-pounds. It's like, yeah, no, but that's easy. That's easy to calculate because that's force equals ma, and like this is given loss. It's like it's good at transferring this amount of power because it has this amount of loss of percent, and this amount of heat, of course, is usually what that loss is, and this amount of friction is usually what that loss really means for this type of gapping and tolerance, right? So it's like, well, these given pressures for this given acceleration for this given type of force, then applied over this given period of time, then gives you this amount of torque when it's done this many number of times in a given second. And what do you know? All of a sudden, you can kind of piece together how the fuck that stupid, idiotic, complicated mess of a mathematical equation that you look up on Google for how do you calculate for engine torque for given heat and pressures inside of a cylinder is really ultimately trying to tell you. It's like, this is your time, this is your pressure, this is your density, this is your acceleration, and this is your given mass. This is your given loss to your given crank. That's all it's trying to tell you. Calculating for that, you get 900 foot-pounds of torque. If you know anything about how to do that math, the material, pressures, and everything, you can work back to various engine designs for four cylinders. That's all we're talking about. Post piston, box, looking motherfucker that I just described easily in such a way that you'd probably be able to put it together yourself. You can now know, because it's going to look like it's under square, right? How best to go about those calculations for the exhaust recirculation, recycling, and into the turbine. What the turbine really is, instead of what you might have thought it would have been, and even how to calculate for that for greatest amounts of efficiency. How to ultimately situate the given loss, axle profiles, and gearing, and what gearing you're probably going to need to have, as I described it. And in fact, you're going to come up with several different engine designs and displacements. So I'll tell you what the displacement is. It's the new F1 regulations engine. I think it's like 1.6 or 1.8 liters or some shit. Now, I'm working off of their fuel flow rate restrictions. I wanted to see if I could beat their designers. Their engine designers get paid a lot, and I'm like, yeah, okay. But also, what if they weren't that good? What if I could beat you? What if I could beat you with a modular engine that's cheap as fuck? I don't need to spend $10 million to go compete. Working off of their fuel flow rates, the fuel they use, right? basic bitch engine oil, right? And compression ratios that are likely something I can actually use and not be insane to think of trying, right? Right. Then you end up realizing, oh yeah, 900 foot-pounds of torque is easy, right? It's gonna weigh less than them. It's gonna be more compact and more efficient. The secret sauce was all along, guys. I have multiple injector timing types and a nitrogen filter. Shockingly. They didn't consider the one trick that'll make it all work better. Just filter out nitrogen, man. Perform a little work energy, dude. Like, what's the problem? Make that work energy do more work energy for your work energy. Make yourself more efficient. Now, granted, I am being a bit of a dick about it, but it is essentially going to work off of that. It's like, look, because oxygen is here, that means your fuel burns far hotter and is now more efficient at capturing heat to work. Because I can add in the nitrogen that I have to worry about it attaching to any of the other fuel that was burnt, making your carbon dioxide and H2O be what it is. I don't have to worry about nitric oxides. But that also means that heat for nitrogen is very efficiently recaptured into producing work energy for you. Because it's so compact, because it's right above you, and then that's its own timing, right? I don't have to worry about a whole bunch more in terms of I need, what is this? Two heavy ass camshafts? Nah, no, that's my intake manifold. Why would I use anything else? It's like I already have to cool this sucker. Might as well put it right next to it, right? That's what I'm gonna do. But of course, it's a boxy inline. It's not an inline four. It wouldn't fit their rules. But like, man, could smoke him with this. But I could make an inline four off of this instead of making it modular, though. For what it's worth, I just have to, build it all off of that. I don't know. At that point, it's like, well, if you're gonna spend 10 million, dude, I'm just gonna freaking get out the thermophotovoltaic and the thermoelectric generating materials, put some solenoid areas, you know, and then put some like, electric charge variance areas, so it's basically like ionic, right? And then try and make like because the fuel combusted, effectively a type of fuel cell, right? Electron redox flow or electron, work energy because it's a battery at that moment in time, even though I created a heat. It's like, right, but during that, electrons are moving, and so they'll want to come back, and that creates a solenoid. The heat gets recaptured, gets placed back into effectively moving the thing along with the heat recapturing, and then I just do the inline four kind of system the same essentially, and then have the turbine directly underneath, right? And then, well, I can't do a, you know, a post piston, which I would love. Those pistons are so good. Yeah, but no, I'd be able to get more close to a square design ish, right? It's still gonna be under square, but it's closer. Yeah. And then I have a bottom that allows for the exhaust recirculation, but then it's like the turbine can effectively be attached to a gearing that's basically a part of the crank. The crank is the gear, turbine is the gear, right? kind of thing, and then that goes directly to the transmission. Then that can run the intake manifold instead of using poppet valves, because I hate poppet valves. Poppet valves are not my jam. They are not my jam. If you have to, it's like, all right, then it's Ducati setup, and then I just move where the little, places where it hits the bumps on the rotating part, right, of the intake manifold, because it's like that's going to help separate the nitrogen and the oxygen, and also still give it cooling before it gets placed into the cylinder, right? So, but it's also a compressor. So if you don't know, that one's a more trick setup. So it goes through the center, that's where the nitrogen is. It's then going to get separated by doing that. That also takes hot nitrogen, exchanges it, fresh exchange, but then I also have a cooling intake like the velocity stacks, but that's really just a bunch of cooling, right? And then it's Ducati, so to open it up with hydraulic instead of a ramrod, like a hard, right? It's going to be hydraulic, so to open it up with hydraulic fluid, and then it'll close it using hydraulic fluid, using that pressure system, and then they're just going to be connected using a rail that balances off of its intake and exhaust timing. So if you don't know, the exhaust needs to also get fed in with the nitrogen. So as the exhaust goes off, then the nitrogen intake to that exhaust, as it's already flowing, would then get pushed into that exhaust, but then we're still going to be pushing exhaust into the turbine as well. And then I can run with the fuel flow restrictions the nitrogen six stroke, right? And then I can intake as it's already moved some of that nitrogen through into the exhaust. Then when it opens for scavenge, force in nitrogen, exhaust goes out, cools it off, nitrogen comes in, there's exhaust at the bottom. That's, of course, hot. Oof, you want that though, right? But now it's like, right, yeah, but this other thing's combusting. And oh, by the way, the valve is finally open at the bottom. It's been re-ish pressurized, right? There's the nitrogen. But it's like, right, yeah, but we're already going to move this, and you're quite hot. You don't really want to be there. And there's a lower pressure over here, sucks it out. You know what I mean? And then it's like, that's going to help bring down the piston head, right? And that intakes nitrogen, which helps cools off which helps to cool off the cylinder. And that's a good thing. You don't want that. That also means that you don't have a power stroke during that, right? Right, yeah, except I have a power stroke from my exhaust going into my turbine, which directly goes into my crank. Yep. And then it's like, right, right. By the way, nitrogen's like definitely not ionic, right? It's like, well, you can make it ionic if you wanted to, or you can make it not have enough electrons, right? If you don't know, that means, ooh, I might want electrons to go to that, right? Comparatively to somewhere else. That makes electrons do work. That makes solenoids do work. That makes the heat generated and the pressure, thermoelectric, thermophotovoltaic, and the piezoelectric, which of course we have to cool it still, but still, all of that allows for it to move the crank, which the crank at this point is effectively the electric motor, right? Along with the pistons themselves, right? All super hardcore compact stuff. My thermal efficiencies went way, way up. My electric motor efficiencies went way up too, which is good, especially since I can still cool the piston by making it a little bit hollow and making it a little bit fatter for the connecting rod. Because it's only ever going to go directly up and down, which is a good thing. You don't need anything else sliding. Now harmonic balances are taken care of for a inline 4. And now it looks a little bit fatter. What do you got this piece on the side for? Shut up. You didn't see nothing. Meanwhile, fuel flow restrictions, I'm good to go. My thermal efficiencies went so high, especially because that turbine can also use that along with the shrouding, right? For the thermal photovoltaic, and or in this instance, thermoelectric and piezoelectric. Because thermal photovoltaic would mostly be the exhaust side that's trying to send it back to the bottom, or directly adjacent to the turbine or where that area is because it just doesn't get hot enough for thermal photovoltaic past a point. It's going to keep cooling, which is fine. We're fine with it being cold. It starts off with high oxygen rich air, which gets real hot real fast. So that's not that bad. It's the fact that by the time it gets out to the exhaust, that you have to worry more than anything about it condensing to such a degree that it has water vapor constantly coming out the exhaust. So my general rule of thumb was to always add in intake with a Bernoulli principles type of design from the diffusers in the bottom and the radiators, which are waste heat radiators for the side pods, right? Which most of the time they're at the bottom where the diffusers are. As they go through, they then expand even further, which of course increases the amount of downforce you receive. As they go into the exhaust, of course, it's not a movable piece. What is it? It's a constant air pump, though. Sure is. That makes downforce. But only when you're revving high enough and only when you're traveling fast enough. But no moving pieces are going on. Basic valving. Nope, no valving. It's called physics. They really hate this one trick called no, your rules state this, and I'm not breaking a single one of them. At all, I know, but fuck you. I'd say that you are. No. I have to exhaust anyways. Yeah, but you already push air through these little side pod areas with your freaking exhaust right now in the rear. I can see that easily with the little shroud in the rear of that car you've got. Why do you think you have a big wide open gap area around your exhaust? Come on. I can do this. There's nothing wrong with this. You're allowed to have radiators there. You're allowed to have radiators wherever you can put radiators, technically speaking. Yeah. Wait, what? I have a lot of radiators everywhere. A lot of small ass radiators everywhere. Meanwhile, they're also piezoelectric Stirling heat exchanger, Joe Thompson acoustic resonance heat exchanger radiators. Yeah. But that's also the skin in a lot of ways. It's like, no. These areas are very unlikely to get, hit in such a way ever, really, pretty much. So I don't ever have to worry about that, right? So that's fine. Yeah. But, you still should worry you don't get hit, but still. Then there's always these little small ones, and it's fine if they get hit. But at the same time, I'd prefer if you didn't. Well, I'll try. All right, thank you. There we go. Now we're making progress. It's like, no, those can go, and you'll still be able to keep going. But yeah, you also don't really maybe have this wing anymore. Maybe you don't have this your front end practically anymore. Maybe you want that. I don't know. I'm just saying. Well, I would want that. That's a fair point. Yeah. But yeah, no, it's like with their fuel flow restrictions, it's like, yeah, no, I could do this. Right. And if they're willing to spend $10 million, screw doing what they do normally. I'm gonna do it this way. And I already have the modular, so you know what I mean? Like the modular system is like, oh well, if I can put plastic, right? Because it's 3D printing, along with aluminum and steel, right? It's like, well, then I don't need that. I'm gonna get out the thermal photovoltaics. I'm gonna get out the thermoelectrics. I'm gonna get out those piezoelectrics. Oh yeah. I need a little bit of a harder surface on the inside of the cylinder anyways. It's great. I mean, diamond like carbon exists and polycrystalline diamond exists. That's perfect for IR and thermal transfer, right? What? Yeah, no, I'm definitely getting that out. Let's do it. You're paying $10 million. Oh, I can easily make that fit within a $10 million envelope for you. No problem. None whatsoever. Right? And it's like, well, where's your efficiency? Yeah, it's in the 90s at that point. Yeah, that's the thing. Like, it'll be a very highly compact, incredibly thermally efficient engine in the 90, upper 90, when it really goes, percent engine of efficiency. But that's because I have polycrystalline and diamond-like carbon and very, very low friction and high degrees of thermal and electrical conductivity, heat transfer to work energy, and all the rest that I really kind of need to make that work. Even with the radiators. I mean, that's a really good thermally efficient radiator. If it's gonna get rid of the heat, I might as well turn it into electricity that I'm using anyways, right? And downforce. Well, yeah, I right? And it's like, right, you're gonna have a lot of downforce, even when you go real slow. You're gonna have a lot of power right off the line. Because those electric motors that are in between any given power stroke are gonna make up for any and all power gaps, which is great. 6 stroke, slightly less. I'll make it up with the electric motor. Except, no, you see, it's not the electric motor that you give us to run with a boost, right? That works off of burning incombustible fuel. That is correct. There you go. The engine itself is so efficient, I'm able to do that and make it act like it's a genuine electric motor that has a constant torque and horsepower figure at any given moment that we want it to, right? That smooth power delivery of an electric motor. You can't really tell the difference. But see, I'm allowed to have these batteries because it doesn't use anything with your batteries. And still regenerative brake and still, right, use that electric motor that I can attach to this whole setup and system, power platform, right? As per normal, because that's what the rules state. That's a separate electric motor. Yep. Battery system. So that's good. Meanwhile, it's like, where are the batteries, the capacitors? What are you talking about? I have gas. I have fuel. material in between any of it for the engine. That's capacitors, that's batteries, that's everything I need. I can dump it in, still make it run all the same amount that I always want. What's that waste heat doing now for me? Yeah, making me as efficient as possible. Literally, as best I can, right? It's like, yeah, no, do I need it to be whatever liter? Like, I mean, nothing says I need to run constantly at 25 or whatever amounts of K they want me at. But at the same time, it's like, no, no, I don't think you get it though. I can absolutely do all of that. There's nothing stating I can't do way too high of a figure of torque and horsepower from that fuel. Yeah, but that's what a 90 to upper 90% efficiency engine will get you. That level of efficiency of engine that's going to weigh less than theirs, that's going to produce downforce with no moving parts at all, that's going to literally have much higher torque figures because I can make that electricity do work. It's like 900 was for that. This would easily get you into those 15 to 1800 foot-pounds. You know what I mean? And I can hit much higher RPMs. I don't need it to live and survive for a really long time. I need it to be reliable for an entire race or multiples, really, is what the point is. I don't need it to last for an entire engine life, like for a vehicle, standard every day. So that turns it into, yeah, I don't know if you know this, but the amount of energy you have from your fuel that you can get is incredible when you really break it down. You know what I mean? You have so much on that meat. You know what I mean? Like you said, it was a bone. It's like, what bone? I'm still seeing meat. But you only pick the best of the meat? Like, what's going on here? If you're in my household, you'd be like, you need to eat the rest of that chicken leg. There's so much more meat on that chicken leg. Where? Why aren't you eating all of that? But that's a joke, right? Let's talk about a modular engine block system, and it's like, yeah, no, that's because it is, right? It's like, yeah, that's the point. If you didn't notice, it's like, well, yeah, I can absolutely strap a second inline four to this and then get a V8 easily. It's like, well, we're, gonna do Le Mans or any other kind of racing. I don't need more power. No, 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 come on. Come on. You sure you don't need more power? Okay, you. But I mean, come on. It's only well past 5,000 horsepower here. So you do a basic calculator, right? For like horsepower and torque. See, here's the horsepower spacer parts. I love this guy's calculator. I use it all the time. Yeah, it's pretty nice. Right. Right. Give me the calculator. So let's say it was 1560 easy, right? And then it was we hit 2450 580, right? It's like that's apparently 7,301 horses. And it's like, yeah, no, I can hit that and it'll survive because it's strong enough. And it's like I was saying, do you want to run at that horsepower? You know what I mean? Do you want to? Like, I'm just spitballing here. Do you need 25,000 RPM? Yeah. I don't. If you want to, I guess, because it's ridiculous, right? At that level, and uh, it's kind of scary when you really break it down. So what does that mean at the end of the straight? Like, right? Like, what does it mean for over 7,000 horsepower vehicle at the end of a mile and a half straight? Oof. Like, we barely survive with the clutch and all the rest setups that we have for funny cars and top fuel drag racers, right? It would be pretty amazing to see a over 300 mile an hour, well and truly past 300. I wouldn't doubt it would be in those 400s if you launched right and you're going for the whole mile long, right? And you had the gear, you had all of that. You even reduced some of that drag. I'm sure you could probably see those 400s. People don't, I think, maybe understand, regular everyday people. If you're here from that and you know anything about engineering and any of that, you don't have to be a Formula One, but you're just a person that knows the reaction time alone is in every way impossible to do anything with. Like, it's so fast, so much mass, even though it's not actually that much because you weigh like very little comparatively. But because of how fast you're traveling, because of everything, it's that level of dangerous now. You know what I mean? Like, you could be in those 400s and you might actually need to stop at that mile, even though you could very well be a half mile away to the brake zone just because of how fast you're traveling. But it's always that balance act. It's like, yeah, no, initially I have to start slowing down, right? And it's like, right, that's called coasting. Oh, at 400 plus miles an hour? Yeah. Oh no, I have so many of the energies of my regeneratives. Let me just. Is this that much kinetic? Force equal ma square, because the acceleration, or in this instance, e acceleration, is such that your kinetic battery, well, it's been squared, right? The mass remains the same, but the force has gone up. It's effectively all it is. So, really rather simple, but it's the dangerous of Yeah, no, I don't think anybody maybe understands that you'd be traveling so fast and you'd be traveling to that speed so quickly and decelerating. You need to be able to decelerate so quickly that you become dangerous to be around on the track. If you, in the slightest, have an issue, you are probably going to be crashing and others are going to be taken with you. And because of the way tracks are set up, there's also the very real possibility you might go through a barrier. So, you know, it's dangerous. I just want to preference that. It's like, oh yeah, no, I can totally give you an engine that's, you'll win all day with it. It's no issues, right? Can you drive? Can you stop? Are you actually able to handle this? Because I'm just letting you know, it's probably not worth it to have 25K with your fuel that you're allowing for. Because I can absolutely hit that. You know what I mean? I just don't think you want to. 100 miles an hour? Yeah, yeah, no. I mean, that's aerodynamics, lightness, and a mile of distance to do it on some of those tracks. So 7,000 plus horsepower will get you there. Yeah. Ugh, God. Ugh. No, for me, that was my aerodynamic trick. I have my aerodynamic trick, which is like, yeah, no, at first it's downforce, and then it's like, right, but once it hits a certain point of exchange rate, and because we're at the high speed and we're at these changes of density, and then all of a sudden I'm forcing more and more of that exhaust through, it changes to a, yeah, well, you got enough downforce, that's not a problem. But we're creating effectively more and more of a bubble of air that's hot around you. That's just gonna create like a real teardroppy like shape. It's like, no worries, you've got the grip, you got the downforce. It's more than enough. But you have a lot less drag than you thought once you hit those speeds, which is around that 140 to 150 mile an hour range. Yeah. The moment you curve, though, it alters and it sucks in. So it's like when it's in a straight, it's like, oh yeah, no, it becomes a little bit more fluid, flowy, like a laminar. Like it consistently does this. The moment you curve, it's coming off because maintaining mass of airflow still happens. It then gets energized to effectively curve and become turbulent and create more of that downforce where you need it. And so, like, as you turn at really high speed, oh yeah, you got more than enough downforce, but you also have a fuck ton of mechanical grip, right? But the moment you're going down just in a straight line, is the moment it turns into, well, you've been going far enough for long enough. I suppose you don't need that much. Ah! Is all I can see like a driver after a point there. You know what I mean? It's like we're Mm. Usually there's this resistance past the point. Yeah, keeps pulling, doesn't it? It does. Yeah, you're gonna love this one. It's just the braking at that point. Yeah, it's the most terrifying part, right? Like it's fine. You can just off to the side, boom, right? It's the braking that gets you every time because it's gonna be one of those moments where like, no, no, that's 50 yards or 50 meters, whatever it was, and you can break. It's like 400 miles an hour plus. I don't know, man. I you can get closer to that 50, but you're not gonna do it at 50. No, it's just not a thing. There's traction, there's friction, there's coefficient rule things. I can still do an aerodynamic kind of like you hit the brake or you take your foot off the gas, and then that's the exhaust stuff, right? And so it's like all of a sudden it becomes less aerodynamically uh teardroppy, right? So you get your drag back, and it's like then you can hit your brake as it hits into, yeah, no, it's starting to slow down, right? And then it's like, how fast though is really going to determine, uh, well, for the aerodynamicists, the braking and suspension experts, and all of that itself, based upon all of those other parameters, I don't think you can ever get near 50. Just FYI. Like, I would be that guy that goes, so 200 meters, huh? That's really fucking amazing. 200 meters? You managed to do that? 200? You were going faster than 450 miles an hour, dude. Like, I'm just letting you know. 450 miles an hour is not slow. In 200 meters, you did a freaking hairpin. Do you know what G-force you hit? I know what G-force you hit. It was over 7 G's. Face just sucked forward. They got the duck lips just from driving. Anyways, but we're talking about a modular engine block system. And it's like, well, the basic premise is this, but then you have to remember the basic premise isn't completely just that, right? I have to develop it a little bit more as a concept. This is the first initial, beginning, because it's like, well, what's the latch system about? It's like, oh, you slide it in from a side, and then you go either down or up, right? And then like you're just gonna have it, latch as a result of that, and then you press a button, right? And then that'll stick the prongs for the quick disconnect into it, right? And then that'll keep it from going outwards. They just have to be a little bit thicker and stronger, right? But then the latch is same thing, right? And then that in its own right just needs a little bit of a gasket material. Make sure it's real nice and tolerant. Then it's all about the girdle and or just the crank and the heads, right? So, but I mean that's easy. If you want to be a bit of a dick to certain manufacturers, it's like you could just cast that. Like honestly speaking, you could just cast that a little. I'm just saying you can do that, but then I want to move on to, it's like, well, you can cast that, but you could also like do a basic CNC with the 3D printer and a little aluminum, steel, and 3D printer material blends. Strong where you need it, and then light where but still strong where you really need that, kind of shave some of that weight, and then 3D printing infill effectively, where it's essentially just to help make sure everything maintains where it's at, and it looks nice and all the rest of it, and it's still structurally strong enough and very light now where you want it, right? All right, I have to go pee. Bye.